Welcome to Study Loop.
So this question it asks us how many slits per centimeter must a grating have if there is to be no second-order spectrum for any visible wavelengths. Okay, so let's first write down the equation for diffraction grating, which is the same equation as the one for double slit interference. And there is, because sine theta cannot be larger than 1, there is a certain amount of m that could possibly exist. And in this case, it asks us no second-order spectrum. So that means the only possible m that we could possibly observe is 0 and 1. We cannot observe anything at m equals 2. So let's say sine theta is equal to m lambda over d. What we need to know is what lambda we should be using. This question says we cannot see m equals 2 for any visible wavelengths. So the wavelength range for visible light, it's around 400 nanometer to around 750 nanometer. So if this thing sine theta has to be small or equal to 1, so what we get is that the smaller the lambda, the larger the m. So when this thing equals to 1, and we have 400 nanometer, maybe we can have m equals 3 for 400 nanometer, but maybe we can only have m equals 2 for 750 nanometer, because what happens is that when the wavelength increases, the angle increases, so the pattern will be more spread out. So right now, we want to make sure we don't see the spectrum for any single visible light. So we want to make sure, so this 400 nanometer will be our limit, because usually we tend to see more orders for shorter wavelengths than we do for the longer wavelengths. So we are constrained by 400 nanometer instead of the 750 nanometer. So that's why we should be using 400 nanometer here, because in other words, what I'm saying is that if we want to make sure if we are sure we are not going to see second order spectrum for 400 nanometer, then we are 100% sure that we won't see second order spectrum for any other wavelengths larger than 400 nanometer. That's why we should be using the lowest wavelength of the visible light to find out the slits per centimeter that we're looking for. So enough of that. Let's find the critical value for D. So what is a D, so that when we have that D, we can just see the second order spectrum for 400 nanometer. That D we're looking for is m lambda over sine theta equals 2 times 400 nanometer over 1. That gives us 800 nanometer. So this is a critical value. So this is maximum slits per centimeter we can have if we want to make sure we just see the second order spectrum for the lowest possible wavelengths for the visible light. So if we want to make sure there's no second order spectrum, what we want is D smaller than 800 nanometer. Okay, so but we are not, D is the separation between two slits. Right now we're asked how many slits per centimeter. So we should be looking for 1 over D. So that is 1 over 800 nanometer is 8 times 10 to the negative 7 meter. And that gives us 1.25 times 10 to the 6 per meter, which is equal to per centimeter. So we want 12,500 slits per centimeter, and this is a minimum amount. Yes, this is a minimum amount of slits we want per centimeter, and we for any slits denser than that, if we have more slits, then that guarantees that we will not be able to see any second order spectrum for any of the visible wavelengths.